Welcome to 6.4 Logarithmic Equations. In this video, we will be solving 6 logarithmic equations, but before we get started, I highly recommend that you have your notes from 6.2, Properties of Logarithms, readily available, and because we are going to be using a lot of those properties that we learned in this chapter in order to solve these equations. So I know we don't have them all completely memorized. I have the ones that we're going to be using here on this page. These are nice screen grabs that I found from different websites, so they're not using the exact same way that I wrote them in that video, but you get the idea. We're going to be using the one-to-one property, which is a pretty obvious idea. If you have two logs equal to each other with no other terms and they have the same base, then their insides must equal to each other. Then an idea that we've learned from the very beginning of the chapter is converting between log form and exponential form. We'll be using that in a lot of these. Then the properties of logarithms help us to condense logarithmic two terms that have logs in them, such as the product property of logs, the quotient property of logs, and also the power property that says we can bring that exponent out front. Then the last thing that we're going to be using is the change of base formula. If our two logs don't have the same base in order to use any of these properties, we can change that base to make it what we want. So we're going to be using these properties to solve 6 log equations. Let's get started. Here in number 1, we have a log equal to a log, no extra terms. The bases are the same, base 117, and I put this in here just to show that we're going to be using the one-to-one property. We clearly have a log base a of x equals log base a of y here. Here's our x, here's our y. So what we can do is, because we have the same base on both sides, we can essentially drop that and just set what's called technically the arguments. The arguments are just what's on the inside. So we can set 1 minus 3x equal to x squared minus 3. Once we have this, we see that we're going to have a quadratic, and we want to set the quadratic to 0 and keep the quadratic term positive. So the quadratic term is positive on the right-hand side. So I'm going to subtract 1 and add 3x to both sides. So we have x squared, that's not bothered, then plus 3x, then negative 3 minus 1 is minus 4, and we have it equal to 0. This is a good rule of thumb with quadratics. Set it equal to 0, see if you can factor it. In this case, we can. We have x plus 4 and x minus 1 as our two factors. And then we'll have x can potentially equal negative 4 or potentially equals 1. I say potentially because the domain of logarithmic functions, log base b of x, whatever's on the inside here, remember, needs to be positive. So let's check our answers and make sure that they yield positive results inside our log. If we plug in negative 4, so we'll check in blue here. If we plug in negative 4, we'll have log, it doesn't matter the base, of 1 minus 3 times negative 4. Is what's inside here positive? Yes. So we're okay on that side. Let's check the other side. It's log base whatever, it does not matter. We're just checking that the inside's positive. And if we plug in negative 4, we'll square it, and then minus 3. Is what's inside here positive? Yes. So negative 4 is a viable solution. Let's check x equals 1. Plugging in 1, we'll have log base 117. Doesn't matter the base though. We care about what's on the inside. Is that positive? We'll have 1 minus 3 times 1. And that's a negative number. So we're asked, is this positive? No. Therefore, plugging in 1 doesn't work. Plugging in 1 over here also doesn't work. It yields a negative number inside the log function. So 1 cannot work. With problems that have restricted domains, like logarithmic functions have a restricted domain, we do always have to check to make sure that the answers that we get from just the pure mathematics works in the context of the specific problem we're dealing with. When we had exponential equations, we didn't have any issues with that because we can plug in any number into an exponential equation. The domain's all real numbers. For logarithmic functions, however, our domain is not all real numbers. We have potential restrictions. We do have restrictions on the domain, so potentially some of these x values we get might not work. Therefore, we do have to check our final answers and make sure what's inside is positive. So negative 4 is our only solution. Problem number 2, we only have one log in this problem. We don't have two of them. So what we want to do is isolate the log. So we're going to end up using log to exponential form here when we have only the one log. So let's isolate our logarithm. I'm going to do that by subtracting 2. So we'll have negative the natural log of x minus 3 equals negative 1. And after that, I want to divide both sides by negative 1, so I can isolate the log. So the natural log of x minus 3 equals 1. So I isolated the logarithm. We only had one logarithm. So now we can clearly see that we have a logarithmic form of an equation, and we want to get that to an exponential form so we can solve for the x. Remember, with natural log, the base is e. So we'll have e to the first equals x minus 3. E to the first is just e, so we'll have e plus 3 equals x. E is about 2.7, so a good answer is just e plus 3. That's a totally fine answer. If you wanted to write it as a decimal approximation, e is 2.718, so adding 3 onto that, we'll have approximately 5.718. So we can write this either or. The reason that I kept it as e plus 3 is e is such a specific number in mathematics. It's similar to how we treat pi. And so pi is very rarely written as its decimal. It's normally just written as pi. So e is very similar in that way. So writing an answer as e plus 3 is most likely more common to be seen rather than its decimal approximation. Just FYI. Okay, let's take a look at problem number 3. We have two logs, but it's not the same as the first problem. It's not log equals log. In this case, we have an extra term there. Because we have 3 terms, we want to get these 2 log terms down to 1 log term. Once we get it down to 1 log term, we have it in log form and we can write it in exponential form, much like number 2. We're actually going to use a property of logarithms. If we look, we have a log base 6 plus another log base 6. That is the product property expanded. We have this over here. So this is our m, and 3 minus x is our n. We can write it as one single log base 6 and multiply. Let's do that. So we'll have this as log base 6, and then we want to multiply x plus 4 times 3 minus x, and that equals 1. So we used our power property, our product property of logarithms in order to write this as a single log. What I'm going to do before going into exponential form is I'm going to simplify this by multiplying it out on the inside. So we'll have log base 6, and then on the inside we'll multiply the x through, so we'll have 3x minus x squared. Then we'll multiply the 4 through, so plus 12 minus 4x. Again, cleaning it up a little bit by combining like terms will give us negative x squared minus x plus 12, and that'll equal 1. So now we used our property of logarithms to condense into a single log term. That log term is isolated, and we have this equation in log form. Now we can go into exponential form. Our base is 6, exponent's 1, and it equals this inside piece here. Negative x squared minus x plus 12. Again, we have a quadratic. I'm going to actually add x squared to both sides so we can get that squared term positive. So I'm going to move everything to the left-hand side of the equation through addition and subtraction. So we'll add x squared to both sides. We'll add x to both sides. And then I'm going to subtract 12. This is just 6. 6 minus 12 is minus 6. Now we have a quadratic that we can factor because it's equal to 0. It's going to be two numbers that multiply to negative 6 that add up to positive 1, so plus 3 and minus 2. Our solutions are potentially negative 3 and 2. Again, I say potentially because we do have to double check our work and make sure that it works. So if we plug in negative 3 into our initial logs here, if we plug in negative 3, we'll have log base whatever of negative 3 plus 4. that works. And then we'll have log, and then on the inside, 3 minus negative 3. So both of those insides are positive, therefore negative 3 is a viable solution. Next, we want to check x equals 2. We'll see if that one works, aka does it make, what's inside the log positive. So when we plug in 2, we'll have 2 plus 4 on the inside, that's positive. And then here we'll have 3 minus 2. That's also positive. So both of these solutions end up working. In problem number 4, we see, once again, just like problem 3, we have 3 terms. 2 of them are log terms. So let's get those log terms on the same side of the equal sign just by themselves, and then see if we can simplify them by condensing them using properties of logs. So I'm going to add log base 7 of 3 minus x to both sides. So on this side, I still have a 1. Over here, I'm adding 2 logs together with the same base. Just like in problem number 3, we're going to use the property of logs, the product property of logs, that says if we're adding 2 logs together with the same base, it's really one single log with that base and multiplying what's inside. So we're going to multiply 1 minus 2x by 3 minus x. So we have condensed these 2 log terms into one log term using our properties of logs. Now that we have it in log form, we can go ahead and rewrite an exponential form. However, real quick, before we do that, I just want to simplify this on the inside. We're going to simplify through multiplication and combining like terms. So we'll distribute the 1 through, so we'll have 3 minus x, then distribute the negative 2x through, so we'll have minus 6x plus 2x squared. Then combining like terms and just writing it in a more standard way, we'll have 2x squared minus 7x plus 3 equals 1. So now that we're in log form, we want to go ahead and write it in exponential form. Once you have something in log form, you do want to write it in exponential form in order to solve for the x. So we have our base of 7, it's raised to the first power, and it equals here what's on the inside, 2x squared minus 7x plus 3. Since we have a quadratic, we want to set our quadratic equal to 0 to solve. So doing that, I'm just going to subtract 7 from both sides to keep our quadratic term positive. So 2x squared minus 7x, and then 3 minus 7 is minus 4. Now here, we do have a factorable quadratic. We'll multiply 2 times negative 4. We want 2 numbers that multiply to negative 8 that add up to negative 7. So 2 numbers that multiply to negative 8 that add to negative 7. Multiply to negative 8, add to negative 7. Let's see, those will be negative 8 and 1. So we'll rewrite as 2x squared minus 8x plus 1x minus 4. Then we can factor by grouping. So our first 2, we'll factor the GCF of 2x out, and we're left with x minus 4. Our second group of 2 terms, the 1x minus 4, we'll factor out a plus 1, and we're again left with x minus 4. From here, we take the stuff on the outside, 2x plus 1, and the stuff on the inside, x minus 4. From here, we set each factor to 0, so 2x minus 1 getting set equal to 0 will provide us with a potential solution of negative 1/2. X minus 4 equals 0 will provide us with a potential solution of negative 1/2. Again, I say potential solutions because we need to check and make sure that these answers allow our logs to still have a positive inside. So if we take a look at the very beginning, our 2 log terms have a 1 minus 2x on the inside and a 3 minus x on the inside. So I'm going to check x equals negative 1/2 and make sure that it keeps what's on the inside positive. So let's check this. We'll have log base, it doesn't matter, but base 7 of 1 minus 2 times negative 1/2. Is this positive? Yes. Negative times a negative is positive, so it keeps what's on the inside here positive. So check. Then let's check the other log, log base 7 of 3 minus x, so 3 minus negative half. Yep, that's also a positive input there. So negative 1/2 is a viable solution. Next, we want to check x equals 4. So plugging in 4, already I see an issue, just as I'm erasing here, I see an issue. So plugging in 4, we'll have 1 minus 2 times 4. That's a negative number. So is it positive? No, it does not work. So this is not a solution. So our only solution here is x equals negative 1/2. In number 5, we again have a problem that looks similar to numbers 3 and 4. We have 3 terms total. 2 of them are a log, and they have the same base. So what we want to do is get those 2 log terms on the same side just by themselves. So I'm going to do that by subtracting log base 2 of 6 minus x from both sides. So I'll rewrite this out. We'll have log base 2 of x plus 3 minus log base 2 of 6 minus x equals 3. Taking a look at our properties of logarithms, we can see that we have 2 logs being subtracted and they have the same base. So that's our second property, our quotient property of logarithms. Log base b of m minus log base b of n can be condensed into a single log of that same base as the 2 in a fraction. So that's our quotient rule, or quotient property rather. So we can rewrite this as one single log base 2, and then our numerator will be x plus 3 and our denominator will be 6 minus x. So again, we're using properties of logs to condense these 2 logs into a single logarithm. Thank you, properties of logs picture. Now we have our equation in log form. So we want to get it into exponential form. So our base here is 2, our exponent's 3, and it equals this wonderful quotient. So we have 8 equals, again, the wonderful quotient. To solve, you can think about this as 8 over 1 and cross multiply. What a lot of you do is just multiply anyway, so we'll multiply both sides by 6 minus x, which is the same thing essentially as cross multiplying. From here, I'm going to distribute the 8 through, so we'll have 48 minus 8x. These cancel, so we're left with equals x plus 3. From here, I want to get x by itself, so I'm going to add 8x to both sides and also subtract 3 from both sides. So we'll get that x is potentially 5. We do have to plug 5 back in. Let's just check this without writing it out because this is an easy thing to plug back in. So if we check 5, does it make inside here positive? Yeah, 5 plus 3 is positive. Does it make inside here positive? Yes, 6 minus 5 is positive. So x minus 5 is a viable solution. In our last problem, we're going to be pulling out all the stops here. So we have 3 terms again, and 2 of them are logs. So let's get those 2 terms with logs in it on the same side, and we'll keep the 1 isolated. So I'm going to subtract this term, 2 log base 4 of x plus 1 from both sides. So we'll have 1 equals 2 log base 2 of x minus 2 log base 4 of x plus 1. So this is our only problem that our bases have not been the same. Therefore, we want to use the change of base formula. So what we'll do is we'll change this term right here to have a base of 2. We'll get to the smaller base. So our change of base formula says that if we want to change our log base b of a to a different base, say x, we write it as a quotient. It ends up being log base x of what was already on the inside over log base x of the original base. So let's change this using the change of base formula. So this will be minus 2, and then log base 4 of x plus 1 can become log base 2 of x plus 1 over log base 2 of 4. Now we know what log base 2 of 4 is. We can figure that out. 2 to the what gives us 4, that is going to be 2. So this is really minus 2 log base 2 of x plus 1 over 2. This negative 2 and this 2 will end up canceling out to just a minus 1. So this will end up being just minus log base 2 of x plus 1 here. The rest of our problem we can just bring down. So we'll have 1 equals 2 log base 2 of x minus log base 2 of x plus 1. So we've successfully changed our log of base 4 into a log of base 2 using the change of base formula over here. So that one is done. Now we see that we have this 2 out front, so we can simplify this one to just be a log base 2 of something using the power property of logarithms that says if you have a number out in front, that's really the exponent of what's on the inside. So I'm going to rewrite this first log term as log base 2 of x squared. Then we'll again have minus log base 2 of x plus 1. So we have a log base 2 minus another log base 2. That is the expanded version of our quotient property, so we can condense it and write it as a single log base 2 with them as quotients. So we'll have 1 equals log base 2 of x squared over x plus 1. So we've used a lot. We've used this property and this property here. The last thing that we see is that we now have an equation in logarithmic form, and so we can rewrite it into exponential form. So rewriting into exponential form looks like our base of 2 to the first power equals x squared over x plus 1. To solve, we can multiply both sides by x plus 1. This is really just a 2, so we'll distribute the 2 through that x plus 1, and we'll have 2x plus 2 equals x squared. Again, we have a quadratic, so we want to set this quadratic equals to 0. So I'm going to keep that x squared positive over there and subtract the 2x and the 2. So from here we have a quadratic. Let's see if it's factorable. Are there two numbers that multiply to negative 2 that add to negative 2? No, so we need to use the quadratic formula. Using the quadratic formula, our a is 1, our b is negative 2, and our c is negative 2. So we'll have the opposite of b plus or minus the square root of b squared, which is just 4, minus 4 times a times c, all over 2 times a, which is just 2. So we'll have 2 plus or minus, let's see what our discriminant is. This is 4 plus 8, so that's 12 on the inside, all over 2. The square root of 12 gets simplified to root 4 root 3, which is 2 root 3, all over 2. Then our 2's can cancel, so we'll have 1 plus or minus root 3. So I got our original problem since it's been so much time since we've seen it, but here's our original problem. I want to check both of these solutions, 1 plus root 3 and 1 minus root 3. Root 3 is like 1.7, so if we think about adding those, it's like 1 plus 1.7. So if we check 1 plus root 3, that's approximately 2.7. So if we plug in 2.7, is that positive? Yes, inside both. So that one works. So 1 plus root 3 is a viable solution. How about 1 minus root 3? So let's test that one. If we test 1 minus root 3, that's 1 minus approximately 1.7, so it's approximately negative 0.7. If we plug in negative 0.7, that works here, but it doesn't work here because it would be a negative inside. So our only viable solution is 1 plus root 3. Here is something I wrote up real quick. I couldn't find a good graphic organizer online, so here's my own. For solving log equations, this is basically what we did. You kind of have two scenarios in general. The first one was like number 1. This is the simplest one you could get. If you just have two terms, log equals log, and they have the same base, you just want to use that 1-to-1 property and set the insides equal to each other and solve. Other means if we have most likely 3 terms and 2 of them are log terms, we want to use log properties, specifically the product and quotient, to condense those log terms down to 1. Then you want to change from log form into exponential form. In general, once you've done that, you're able to solve pretty easily. Then, no matter what type of problem you have, because log functions have a restricted domain, you need to make sure that you check your solutions to make sure that they actually are viable solutions. We do that by plugging them back in and making sure that what's inside every log term is greater than 0. Congratulations, you can now successfully solve both exponential and logarithmic functions.